Hello, I'm Professor Rad, and this is Precalc video 225, more properties of logarithms. So a couple videos ago, we found a list of several properties of logarithmic functions, and they were based off of properties of exponential functions and the fact that logarithmic functions and exponential functions are inverses of each other. Then in our last video, we started to develop a few more properties. So actually properties 1, 2, and 3 that are on the board behind me are the 3 that we developed in the last video. So now we've got a whole bunch of other properties that we're going to look at and talk about. So I'm going to get out of the way. And if you want to pause the video and copy down these 9 properties, you can do that. And then we'll talk about them. All right, so hopefully you took a moment to copy these down. So in these properties, we're basically dealing with positive real numbers. So that's why there's this little plus next to the R. So we're saying all of the variables that are in use for these properties are positive values. And we're going to say that A and B are not 1 because we don't want a base of 1. And we're going to use lowercase a and b as the base of the logarithmic expressions. So as we mentioned, the first 3 we looked at in the last video, and I tried to kind of indicate by color on these properties some of their uses. So these first 2 I put in purple because they relate back to our initial properties over here. So log base a of 1 equals 0 is the x-intercept of a logarithmic function, and log base a of a equals 1 is this point here, our point A1. So they had connections back to our graphical interpretation of logarithmic functions. And here we are looking at them as algebraically. These next 3 properties that are written in red are helpful when you're solving an equation. So we have that log base a of a to the r equals r. This is because logarithmic functions undo the base of an exponential expression. So the log base a and the exponential base a cancel each other out, and you're just left with the exponent, which was r. Property number 4 is doing pretty much the same thing, just in the opposite direction. We have an exponential base of a being raised to a logarithmic base of a. So the exponential base and the logarithmic base cancel each other out, and we're going to be left with just the argument of m. So numbers 3 and 4 are similar in that they're an expression that logarithmic and exponential expressions are inverses of each other. This next one, we're going to see when we go to solve an equation and we have different bases or exponential expressions that have different bases. So if you have a to the x, that's going to equal e to the x natural log of a. And we can prove this statement using some of these other properties in the list. So these 3 are going to be helpful for solving equations. So will properties 6 through 9, but they help us in a different way. They're not like our immediate step into solving, into bringing things out of the land of exponent or outside of the logarithm. Instead, properties 6, 7, and 8 can help us to evaluate exponential expressions. Or if we have an equation that has multiple exponential expressions, it gives us a way to combine them into one so that we end up with log equal to log, so we can set the arguments equal to each other. Just like if we had a to the u equals a to the v, we could set the exponents equal to each other. So this first one, number 6, says that if I have log base a of m to the r, I can bring that r out in front of the logarithmic expression. In other words, I can turn this exponent inside a logarithm into multiplication outside the logarithm. This is similar to property 3, but it's a little bit different because in property 3, the base inside the logarithm and the base of the logarithm were the same, whereas here they are not. For number 7, we have the logarithm of a product can be written as the sum of 2 logarithms. So if you're multiplying inside the logarithm, then you can add those 2 logarithms separately. And then this third one says if you have the log of a quotient, then you can subtract them. So if I have log base a of m over n, that's the same as log base a of m minus log base A of n. Now, I'm not going to do a full proof for these three properties, but I am going to write down some exponential laws that we had. So we have an exponential law that says if I have a to the m times a to the n, that's the same as a to the m plus n. If I have a to the m over a to the n, that's the same as a to the m minus n. And if I have a to the m raised to the r power, that's the same as a to the m times r. Now, our exponential properties we're more familiar with, and I'm putting them here because there's a connection between exponential functions and logarithms. So notice, for example, in this line here, if I am multiplying in the base, then I can add the exponent. With logarithms, if I'm multiplying in the logarithm, then I can add logs. So property 7 and this exponential property have a same kind of connection. They bridge back to each other. Similarly, if I have a quotient with the same base, right? So if I'm dividing my exponential expressions, I can subtract in the exponent. Well, if I'm dividing inside the logarithm, then I can subtract those two logs outside. And similarly here, when I have a power to a power, that's the same as multiplying. Well, when I have a power, I can turn that into multiplication. So these exponential properties that we use to simplify exponential expressions is kind of the background code that makes these three properties function. And then property 9 is really helpful if your calculator is a little bit older, or if you're trying to rewrite an equation so that you have logarithms using the same base. So this is called the change of base formula. Let's say you have a logarithm that's in base 3 and you need it to be in base 5. So you can change it. So if a is 3, I can rewrite it to be in terms of log base 5 by taking the log of the argument over the log of the base. So this is your change of base formula. It's going to be really helpful if you have an older style of a calculator, or if you're solving equations and you need things to be in the same base. So let's do some examples of applying these, because it's all well and good to talk about properties, but until you start applying them, they're just kind of theoretical, right? So let's go ahead and do that. So our properties are listed over here on the left for reference, so we can refer to them as needed. And for this example, we're going to evaluate 3 logarithmic expressions. Now, in the previous video, we talked about one way to evaluate logarithmic expressions, which is setting them up as a logarithmic equation and rewriting them in exponential form. You can still totally do that, but right now, let's see if we can apply the properties to maybe evaluate expressions we couldn't have evaluated before and to shorten up our work a little bit. So for instance, here I have log base 3 of 27. When you're evaluating a logarithmic expression, it's really helpful if you can get the argument, the thing inside the logarithm, in terms of the base of the logarithm as like an exponential expression. So for instance, since our base here is 3 and 27 is the same as 3 cubed, I'm going to rewrite this as log base 3 of 3 cubed. Now we can apply property 3 over here that says the logarithm is going to undo the base. So log base 3 and base of 3 undo each other, and we get the exponent back. So log base 3 of 27 is just 3. For part B, we're going to do a similar thing. So we have log base 16 of 4. This one is tougher because how can you write 4 as a power of 16? Well, I know that 4 squared is going to give me 16. So if I go backwards, that means that 16, if I were to square root 16, I would get 4. So that's one step, I suppose. I can rewrite this as log base 16 of the square root of 16, since the principal square root of 16 will give me back 4. Now, there's a nice connection between radicals and exponents, right? So the square root is the same as the 1/2 power. So this is how we get our exponent for this problem. So log base 16 of 16 to the 1/2. Now we can once again apply property 3 so that the logarithmic base and the base of the exponential expression undo each other, and we get 1/2. Cool, so there we go for part B. Now for part C, this one's trickier because we have a common logarithm. So remember, with a common log, the base is 10. Neither 25 nor 4 is going to be a power of 10, not a nice one. So this technique of applying property 3 is not going to be so helpful here. Similarly, if we were to write this as exponential equations, it wouldn't be really great. So instead of thinking of this as like 2 separate logarithms, let's bring them into one single logarithm. So we're going to use property 7 here because we have a sum of 2 logarithms that have the same base, and we can bring them together into one logarithm by multiplying those arguments. So this is going to be the same as log base 10 of 25 times 4. And again, we're applying property 7. So this was common log has a base of 10, and then 25 is our m, 4 is the n. So here's our 25 times 4. 25 times 4 is 100. And lucky for us, 100 is a power of 10. 100 is 10 squared. So that means this is going to simplify to just 2. Now, if you wanted to write that out in a few more steps, you certainly could. So you could think of this as log base 10 of 10 squared. So that's how we're thinking of it in order to be able to evaluate it here. All right, so now that we've done some exact values of evaluation, let's use our calculators, make sure we're comfortable with the buttons to come up with some approximate values. All righty, so I found my calculator, so we can look at this for reference. Now mine is an older model of the TI-84 Plus. If you have a newer model, I'm going to show you where I believe you can find some of the shorter cut routes. But if we look at this calculator, we'll notice we have an ln button, so we have a natural log button, and we have a log button here. Now this log button here is not like an nth root button where it's like a general logarithmic base. That's the common log. So when you press log on this calculator, what you're really telling it is, I want log base 10. When you type in ln, what you're really telling it is, I want the log base e, natural log. So in the older model, that's as good as it gets. So this calculator that I have I can't input log base 5 specifically. If your calculator has been updated more recently than mine, or you have a newer model, it will. So in that case, I believe if you go to math, it's one of the options listed there. I'm pretty sure that's where it's at. If not, correct me in class. So I'm going to show you if you have one of the older style calculators, or if you have just a standard scientific calculator, how you can figure these out. So like on the standard scientific calculator here, we also have a logarithmic and natural log button, right? So we have those buttons to help us out, same way we did on this older model. So before we use the calculator, first, we want to be accustomed to knowing if our answer is reasonable. So I've got 3 examples. We're going to approximate log of 120, the natural log of 120, and log base 5 of 120. So I'm going to expect this one to probably be pretty close to 2, because the base here is 10, and 10 squared is 100. So 100 is pretty close to 120. And since the logarithm gives me an exponent, I'm going to expect an answer close to 2. So let's approximate these to the nearest thousandth, just so we have a common place to round to. So I'm going to press my common log button and type in 120 and hit equals. And to the nearest thousandth, it's going to give me 2.079. So not too bad. So we have our nice approximation here. Now for this next one, we have our logarithmic function. And so our base is e. Now e is an irrational number about 2.7, so it's close to 3. So if I think of powers of 3, 3 to the 4th is 81. 3 to the 5th is going to be what, 243? So that's too high. So 81 is as close as we're going to get to 120 as a power of 3, because 3 is close to 2.7. So I'm going to expect an answer for this one to probably be close to 4. So let's check it out. So I'm going to do the natural log of 120, and we get 4.787. All right, now this approximation is a little bit further off because we were using 3 instead of E as our point of reference. And 81's further away from 120. Whereas here with the common log, we're able to approximate with the same log base. Now for log base 5 of 120, we've got to think 5 to what power gets me close to 100. So I know that 5 cubed is 125, and that's pretty close to 120. So I'm going to expect log base 5 of 120 to be pretty close to 3. Now the problem is, on my calculator, because it's older, I can't input log base 5. It can't happen. So I'm going to rely on my change of base formula, which was property number 9. In the change of base formula, I'm going to change from log base 5 into either common log or natural log. It doesn't matter, you'll get the same answer either way. So I tend to like natural log only because ln is so much shorter to write than log. Really, that's it. So I'm going to rewrite this using my change of base formula. So this is going to equal, I'm going to say the natural log of 120 over the natural log of 5. When you do your change of base, you're changing from a base of 5 into a new base. In this case, I've chosen base E. And the argument is the argument of the top, and the base is the argument in the bottom. So on my calculator, I'm going to type in the natural log of 120 divided by the natural log of 5, and that will give me an approximation that should be pretty close to 3. So natural log of 120 divided by the natural log of 5, and that gives me 2.975. Now, if your calculator does allow you to input different bases, then you would just go to math, choose the correct menu item, and input your base of 5. But if your calculator doesn't have that, then you're going to need the change of base formula. So if you're using just a regular scientific calculator, that's what you're going to need to use. All right, so that concludes this video on these additional properties of logarithmic functions. In the next couple of videos, we're going to be playing with these 3 properties here, and we're going to be practicing separating out a logarithmic expression and bringing it closer together. Because as you can see, in an instance like this, it was helpful for us to bring these 2 logarithms closer together so we could write with the same base of that logarithm as the exponent. Other times you want to separate stuff out. So like on this one, I need to separate the single log into 2 logs so that I could input it into my calculator. So we'll do some practice applying these properties in our next couple of videos. So I hope you found this helpful with properties of exponents, and I hope you have a wonderful day. So bye for now.